This is lecture 5. Today we discuss some mathematical preliminary results that you have already studied in signals and networks and in basic mathematics course. So these mathematical preliminaries are essential to better understand control analysis. Today we discuss about the function of a complex variable, then analytic function, pole and zero of a function. So I'll be giving you all the formal definitions of these functions. So let us start. What is that function of a complex variable? That is function of a complex variable. So let S be a complex variable. A function of the complex variable Gs, defined as Gs, is represented by its real and imaginary parts. So that is, whenever you have a function that is Gs, S is that complex variable, then we can represent it, that is actually that real part of Gs and the imaginary part of Gs. You all know those things. So now, if we talk about that mapping through that complex function, then how it looks like. So suppose this is your complex plane, that is sigma j omega. So that is actually that S plane. And we have another plane, that is that real of Gs. And here you have that imaginary of Gs. So now, if you take any point here, suppose this is a point in S plane, and if you would like to map through Gs, that is mapping through Gs, so what will you get? So suppose there is another point that is Gs, and this one is mapped from S plane to Gs plane. So now the two definitions should come here. One is which is called single valued function and which is called one-to-one mapping. If for every value of S there is only one corresponding value of Gs, it is called single valued function. That is, if for every value of S there is only one corresponding value, one corresponding value of Gs, then it is called single valued function. Now, if we consider the reverse mapping, that means whenever you take a point here, then if we would like to go back to this S-plane, and if the mapping from GS to S-plane is also single valued, then it is called one-to-one mapping. What is that? If the mapping, I think you all know those things, you have learned it in complex variables and in basic mathematics course. If the mapping from GS to S-plane is also single valued, it is called one-to-one mapping. So in control analysis, we will be considering this type of mapping, one-to-one mapping, and later on you will see that whenever we will do some analysis, stability analysis, we will be considering all single valued function. So I hope at that time you should not be confused about that definitions, because from here you can understand what is single valued function and what is one-to-one mapping. So let us see one example. Let us see one example. Say you have a function that is GS equal to 1 by S plus 1. So here S is that complex variable, and S to GS plane. So in this case, S to GS plane, single valued mapping, because if you take any point in this S plane and then any point in S plane, then you can see that mapping would be that single valued mapping, because if you put any value here, S value here, any value here, S, then you will get a single value of GS. So it is a single valued mapping. But the reverse one means if you take a value here GS, you need to find what is the corresponding value of S so that you will get this GS. That means the reverse mapping is not single valued, but the reverse mapping is not single valued. Why? We have considered here this S plane and GS plane, so including that infinity. So these planes are with infinity points. So then here you can see whenever GS equal to infinity, then we have two values of S. two values of s. So that means when gs equal to infinity, we can have two values of s. One is if you put s equal to 0, then also you will get infinity, as well as if you put s equal to -1, you will get gs equal to infinity. That means this infinite point here, in gs plane, so it is mapped in 2 points. One is that 0 point and another one is coming at -1 point. So you can see here, as infinity is mapped in 2 points, 0 and -1, so it is not a single valued function. So is mapped onto s equal to 0 and s equal to -1. So from this example, you can understand what is called single valued function and what is one-to-one mapping. So it is not one-to-one mapping, because from S plane to GS plane, it is single valued mapping, but in the reverse case, that means mapping from GS to S is not a single valued function. So now we will discuss what is analytic function. So this is very important term, analytic function. I hope you all know it in complex variables. You have studied it in your basic mathematics course. The analytic function, that is the function of complex variable, is said to be analytic in a region of S plane of the function, and that means if the function and its all derivatives exist in that region. So a function of complex variable gs is said to be analytic in a region of S plane if the function and all its derivatives exist in the region. So let us just write the definition of function. A function of complex variable gs is said to be analytic, in a region of S plane. So S plane, that is that complex plane, if the function and all its derivatives exist in the region. So that means if you take consider a region in complex plane, and if you can show that a function exists, that means it does not take any infinite value, so it exists, and all of its derivatives also exist in that region, that means you can say the function is analytic in that region. So let us see one example. Suppose GS is a function, that is S is that complex variable. So here we can see this function would be infinite if you put s equal to 0. So that means if you put s equal to 0, or if you put s equal to -2, so at those 2 points this function would be infinite. That means those are not defined. So we can say that this function is analytic. the function is analytic except s equal to 0 and s equal to -2. Similarly, so this function I have taken a rational function. Similarly, if you take another function, so suppose gs equal to s plus 1. So it is very easy to understand that if you put any values of s here except infinite, so that means if you consider that finite s plane, this function is analytic. So that means it is analytic, and you can also check if you take derivative of that function, so all derivatives would exist. Analytic in finite s plane. So that means this would be only infinite, that if you take s equal to infinity. That means if you consider that finite s plane, this function is analytic. So these are the two definitions, and all through the course I'll be using this term that function is analytic. I hope later on you should not be confused. So now we'll be discussing an important concept, that is pole and zero of a function. So I think all of you have studied poles and zeros of a function in your signals and network course. So here I'll be giving you that formal definition, that is pole and zero of a function. If a function, so let a function gs be analytic and single valued in the neighborhood of a point P. So that means if you take a point in S plane P, and if you consider the neighborhood of that P, and in the neighborhood of that P means excluding that point P, if the function is analytic and single valued, then it is said to have a pole of order R at s equal to P if limit s tends to P, s minus P whole to the power R gs is finite and non-zero. So here first let me just write the definition. So let gs be an analytic and single valued function in the neighborhood of point P. In the neighborhood of point P. So P is a point. So that means P is a point. That means if you just consider the neighborhood of that P, so excluding that P, excluding that point P, so everywhere that function is analytic and single valued function. So it is said to have, a pole of order R at s equal to P if this particular limit, that means when s tends to P, s minus P whole to the power R gs is finite and non-zero. So this is the definition this is the definition of a pole. That means whenever r equal to, say suppose r equal to 1. So that means you have a pole at P. So you have a pole at P. This is a simple pole. That means only one pole is there. This is a simple pole. Similarly, if you have r equal to 2, that means at s equal to P, you have two poles. So that means order 2. So that at the point P, you have two poles. So let us see one example. So that means you have, suppose, GS, and this is that function, rational function. So here, if you apply this particular definition, you can see that simple pole, you have simple pole at s equal to 0. So basically, whenever you have a function like that, just by looking at the denominator, you can see the value of s for which that gs becomes infinite. That means it would be undefined. So those are actually that poles. So whenever you put s equal to 0 here, so then that gs would be infinite. So you have a simple pole at s equal to 0 and pole of order 2 at s equal to -2. That means if you put it here s equal to -2, so this gs would be infinite, and as the order is 2, so that's why the order 2. So gs, so now you can see that gs is analytic in S-plane except at poles. So that means a function is analytic in the S-plane except the poles locations. That means if you exclude those pole locations in the rest of the region, so this function is analytic. So now we'll see the other definition, that is called the zeros of a function. So again, I am telling you all know those things from your signals and networks. So here just I am giving you all the formal definitions, and in control analysis we will be using these terminologies. So if you know these definitions, later on you would not face any problem. So let GS be analytic at S equal to Z. So this is just actually that inverse of that. That means the definition that we have seen in case of pole. So if you take that inverse of that, so it gives you the definition of zeros. So let GS be analytic at S equal to Z. It is said to have a zero of order r, zero of order r at s equal to z if the limit similar to that the definition of pole, that is that limit s tends to z, s minus z, here you can see that this is minus r. That means just inverse of that, gs is finite and non-zero. Finite and non-zero. Or simply we can say that GS has a 0 of order R at S equal to Z if 1 by GS, just if you take that reciprocal of that function 1 by GS, has an Rth order pole at S equal to Z. So that means GS has a 0 of order R at S equal to Z if 1 by GS has an Rth order pole at S equal to Z. So again, this thing would be clear if you see the example. So here we are taking one example. So suppose GS is that plant that is 10 into S plus 2 to S plus 1 S plus 3 whole square. So in this case, you can easily see that the function has poles and zeros, and the easy way is to see that insert the values of S for which that GS becomes 0, that gives you the 0, and the values of S for which that GS becomes infinite, it gives you the poles. So in this particular example, so if you take S equal to minus 2, so then you can see that if you put S equal to minus 2 here, so then you can see GS equal to 0. So that means S equal to minus 2 is a finite 0. Similarly, there are 3 other zeros at infinity. That means if you just expand it, so the order of this one is 4. And now if you divide this numerator and denominator by S to the power 4, then you can see here at S equal to minus 2 it has 1 0. Parallelly, there are 3 other zeros at infinity, because if you put S equal to infinity, again it would be GS would be equal to 0. And what are the pole locations? So one pole is at 0, that is a finite pole. Another pole is at minus 1, and another 2 poles are at minus 3, minus 3. So minus 3 is a pole of order 2. And from here you can see that in this type of rational function, the number of poles is equal to that number of zeros. But if you see, so let us first write it, then I think it would be very clear. That means these poles are here 0 and minus 1, then minus 3, then minus 3. So these poles are all the finite poles, and in case of zeros, you can see that 1 0 is at minus 2, so this is a finite 0, and other zeros are at infinity. So number of poles and number of zeros are same, but the point is the number of zeros here in this case, you have only one finite 0 and other 3 zeros are infinity. So this is an important concept which will be required in control analysis. And whenever a rational function is given to you, you can show the location of poles and zeros via pole zero map. So this is pole zero map. So this particular map is used in control systems. So from this map one can understand where are the locations of poles and zeros for a given rational function. So let us see that pole zero map of this above function. So here the GS that we have taken, that is 10 S plus 2 and then S plus 1 and S plus 3 whole square. So in pole zero map we show the locations of poles and zeros, and those poles and zeros all are the finite poles and zeros. So we do not show the location of poles or zeros at infinite locations. So only we show the location of poles and zeros in finite location. So we use some terminology, some symbol we use in pole zero map. So pole is indicated by cross and zero is indicated by this symbol, small circle. So in this case, particularly in this example, so let us first see what plane it is. So this plane is that sigma j omega, that means this is a complex plane. So now we have a pole here at s equal to, say, s equal to 0. So that means this is that symbol pole. We have shown that the symbol of that pole is cross. Another pole is at -1, so another pole is at -1, and other two poles are at, so it is showing like this. So two poles are there, so this is -3, and then you can see that there is another 0. So 0 is here at -2. So this is actually that pole zero map. And this particular function is also available in MATLAB. Whenever a function is given to you, a rational function is given to you, then if you draw the pole zero map using these two symbols, that means cross and the small circle, then one can understand where are the locations of poles and zeros of a rational function. So let us see what we have discussed so far. So we have started with that function with complex variable, and then we have seen that mapping, single valued mapping and one-to-one mapping, and then we have taken some examples. We have discussed what is the definition of analytic function, and then we have given the concept of poles and zeros. Then we have seen how to present that poles and zeros in a plane, that is that pole zero map. So now I will be giving you just some advantages, disadvantages, and what is that basic concept of Laplace transform. So I think you all are familiar with and expert in Laplace transform because you have studied these things in signals and networks, Laplace transform. So this is actually one transform. So before discussing that Laplace transform, here I am not going to show you the detail of Laplace transform. I think those who forget it, I suggest you to read your class notes of signals and networks. And here just I will be giving you some formulas and some important transforms, Laplace transforms, which will be required to solve that control problems. So Laplace transform, it is a transform. So I think let us first understand what is transform, and it would be very much clear. That means if you see it in case of say logarithm. So suppose you have two numbers. So suppose you have two numbers. Now if you take that logarithm, so if you take that logarithm here, if you take logarithm here, then what you get? You will get that logarithm of that function. So logarithm of numbers, not function. Logarithms of numbers. Now, whenever it is a product of these two numbers, then the logarithm of numbers, basically it gives you that addition. So this is actually that addition, and then here what you get, that is that sum of logarithms. So now if you take anti-logarithms, here, if you take anti-logarithm here, so then you will get that product. So from this particular example, you can understand what we do in case of simple two numbers if we take that product. So first, if you take that logarithm, then it comes into that addition form, and if you take anti-logarithm, then you will get that product. So this product also you can get it through direct classical methods. So direct multiplication by direct multiplication you can also have this product. So basically there are two methods. One is just by direct multiplication you can have it, or you just transform it. So how are you doing this one? So basically you have taken this logarithm and it comes into that addition form, and then if you take anti-logarithm, again you will get back this product. So the same thing we do in case of Laplace transform. So Laplace transform is a transform. So here what we do, say suppose we have that integral differential equation. So let us see what happens in case of Laplace transform. So suppose you have that integral differential integral differential equation means an equation that may contain some derivative and integration. Like in case of say RLC circuit, you can see that whenever you will be writing that equation, that KVL, so it would be V equal to IR plus L di by dt plus 1 by C integration I dt. So that means it consists of derivative and integral. So that is called that integral differential equation. So now if you take that Laplace transform, if you take that Laplace transform, that means you are transforming here So automatically you know that the initial condition is included via this Laplace transform. That is actually the one of the advantages of solving that differential equation using Laplace transform. You need not to solve it separately, that homogeneous equation and particular integral. And then after transform, what we do, just if you do that algebraic manipulation, we get that that reversed transform. So this reversed transform you get just by algebraic manipulation. Just algebraic manipulation. So now how do we get that solution? So solution is obtained just by taking the inverse Laplace transform. So this is very similar to the above one. In case of logarithm, what we do, so two numbers are there, we take logarithm here, and here you can see we take that Laplace transform, and finally what happens in case of logarithmic transform, you see we get the two numbers, product of these two numbers in addition form, and here whenever you take that Laplace transform, it comes into that algebraic form, and then do some algebraic manipulation, you will get it in revised transform. And then if you take inverse Laplace transform, very similar to that anti-logarithm, you will get that solution. So another way of getting the solution is that classical method. You apply the classical method. That means apply the classical method. Apply the classical method and you will get that solution. So this is actually that concept of doing that Laplace transform. And here there is one very important concept. So in this particular case, whenever we do the Laplace transform, so this side is actually done in time domain. And after the Laplace transform, when it comes into that algebraic form, so it becomes frequency domain. So in this course, we will be discussing in detail what is that time domain and that frequency domain. So for the time being, you just take this information that this Laplace transform is very similar to that logarithmic that transform. And here you can see that if you have that integral differential equation, then just by taking Laplace transform and transforming it in algebraic form, we can have that solution via this inverse Laplace transform. And the other method is that classical method. So let us see, that means if we do that Laplace transform, what are the advantage we can have? And I hope you all know those things. Just I am telling to just to recap the theories that you have studied in your signets. So let us see what is that Laplace transform given a real function, say ft, that satisfies this condition. I hope you all know that whether this function is Laplace transformable or not. So then this is that and for some finite for some finite real sigma, for some finite real sigma. So then Fs equal to dt. So this is actually represented at this. This is that Laplace transform. So then here this S is here, that S is called that Laplace variable. S is called that Laplace variable. And you all know that one-sided Laplace transform and both-sided Laplace transform. So one-sided Laplace transform, it makes sense since the systems are causal, and that integration limit here, you can see that integration limit we have taken, that is that 0. So basically this is 0 minus. The reason is we take 0 minus to handle the jump discontinuity at origin. So that means this one-sided Laplace transform. So in control we will be taking one-sided Laplace transform, and it makes sense since the systems are causal. Since the systems are causal, I think you all know that what is causal systems. It depends on that present and the past. It does not depend on future. And the integration, so integration means, say this one, this integration, this integration limit is 0 minus to infinity in order to handle the jump discontinuity. In order to handle the jump discontinuity at origin. So you all know those things. So I am just writing the reason those things should be required when we analyze that control systems. And there are some interesting features of that Laplace transforms that we have discussed here. So those things are, this is actually a mathematical tool, mathematical tool used to solve differential equation, mathematical tool used to solve differential equation. And this is actually that linear ordinary equation. And the homogeneous equation and the particular integral of the solution are obtained in one operation, as you all know. The homogeneous equation and the particular integral of the solution are obtained in one operation. and it converts into algebraic form that we have discussed. It converts. So then it is very helpful. That means whenever that integral differential equation is converted into algebraic form, then it is very easy to handle. And I have already pointed out that means that initial conditions are automatically included via that transformation. So these are all important features of that Laplace transform. So here let us see what we have discussed today, that is the Laplace transform. It is a transform, and we have seen how it is similar to that logarithmic transform. And one important thing is here in case of Laplace transform, before it is the time domain, and after that it is frequency domain that we will be discussing later. And here we have pointed out some features of that Laplace transform, and this is actually the condition for which the functions for which this condition is satisfied, then that function is Laplace transformable. And practically almost all physical signals are Laplace transformable. We can take some functions which are not Laplace transformable, like say ft equal to e to the power a t to the power n. So that is not Laplace transformable, but practically that type of signal does not exist. So mathematically we can say that we can have many functions which are not Laplace transformable, but practically almost all functions are Laplace transformable. We have taken here a one-sided integration, one-sided Laplace transform, and we have taken that 0 minus to handle the jump discontinuity, at origin. And we have seen that this one-sided integral also makes sense as the systems are causal, physical systems that we'll be considering, they are causal. And here we have pointed out one important thing, that means if you would like to solve these equations, integral differential equations, linear ordinary equations via Laplace transform, then that particular integral and homogeneous equations, so those two solutions are obtained through one step. And another thing is via Laplace transform we convert it into the algebraic form. Okay, thank you. So